In this video, we're going to be solving some fluid tank problems in AP Physics 1, Unit 8 Fluids. So a water tank open to the atmosphere has a hole in the side such that water shoots out horizontally as shown in the right. The height of the water above ground is equal to 5.19 meters and the hole is 4.75 meters below the surface. The motion of water surface can be considered negligible when the diameter ratio d exit over d surface is less than 0.44, as in this case. Ignore the friction and the viscosity effects. So we're asked what is the speed of the water coming out the side of the tank. So first let's write down what we have. We were given that the height of the water above the ground was 5.19 meters and the height of the water below the surface is equal to 4.75. So that means that the hole's height above the ground, y initial, is going to be equal to the hole's height above the ground and y initial is this, y naught, and that is equal to 5.19 minus 4.75, which is equal to 0.44 meters. We also know that rho was 1,000 kilograms per meter cubed, and we had our PATM. So because we know that the tank is going to be open to the atmosphere, and also because it exits, so it's open to the atmosphere, and we also see that the water is going to exit when it falls out. That means that the pressure at the surface and at the hole are atmospheric. So at the hole and also at the surface, they're going to be equal to the atmospheric pressure because this is the pressure that they're experiencing on both sides of where they have contact to a place that is not on the wall or a side of the container, so that's exposed to not the inside. So we can write this in our equation. So let's start off with part A. To find the speed of the water coming out the side of the tank, you have to use Bernoulli's equation between the water surface and the hole. So we can write this for our different parts. So when we are at the surface, the pressure is going to equal to PATM. Our V is approximately going to be 0, and our H is going to be H above the hole. So we can just write PATM here. And then when you're at the hole, your pressure is now equal to still PATM. Your V is going to be your speed that we're going to find, and then your H is going to be equal to 0. So we can write Bernoulli's full equation using all these and take these into account. So we have PATM plus rho GH plus 1/2 P0 squared. So this was our surface. And then we have pressure atmospheric plus rho G times 0. So this is going to be when we're at the ground. So this is, when we're at the hole, because that's where we're going to define H as equal to 0. So then we can add 1/2 rho V squared. Now we see that PATM is on both sides. If you subtracted PATM from both sides, it would cancel. That's why we cancel that. So now all we have is, and we also have that this is times 0, so that's equal to 0. This is also equal to 0. So now our equation is pretty simplified down to rho GH is equal to 1/2 rho V squared. You can also cancel out this rho right here because that's on both sides. And then now you just have gravity times height is equal to 1/2 of V squared. So now you can just multiply both sides by 2. You can cancel that out, and then you can take the square root of both sides. So then you get that V is equal to the root of 2GH, just like we've seen in projectile motion as well. So now all we have to do is just substitute in our values. So here V is equal to 2 times 9.8, and our height that we found, the height below the surface was 4.75. So let's highlight this here. Height below the surface. So that's going to be 4.75. And this is equal to 9.65 meters per second, approximately, if you round that. So that's your answer for your V. We're also asked, what is the value of x, the distance the water lands from the edge of the tank? So we're looking for that horizontal distance. We know that the water is going to leave horizontally, so we can think of this with projectile motion. Back to unit 1. So we have our initial horizontal speed, v initial x, which was given as here. We have 9.65 meters per second, which we found over here. So that was your v initial x. And we also have our initial vertical speed, vy initial is equal to 0. And then delta y is equal to the vertical drop to the ground, which is equal to 0.44 m. So we're going to use the vertical motion to find the time. We're going to use the projectile motion equation. Delta y is equal to vy initial t plus 1/2 gt squared. So because vy initial is equal to 0, this whole thing is going to cancel out because of this. So we can just substitute in everything else now. So we're going to have 0.44 is equal to 1/2 times 9.8 times t squared. And this was substituting in this delta y right here. So now you're going to have 0.44 is equal to 4.9 t squared. T squared is equal to 0.44 over 4.9, which is going to be equal to 0.0898. If you take the root of both sides here, you're going to get that t is equal to approximately 0.300 seconds. Now you have to find the horizontal distance. We have x is equal to vx, your velocity x component, times t. So that x component was 9.65. And the time was 0.300. So that is approximately 2.90 meters equal to x. So those are our two answers. Now for our next question, we have a water tank open to the atmosphere and has a hole that shoots water horizontally as shown in the right. So this is going to be the same setup as over here. We can also move this down here. So it's going to be the same setup. We're asked A, what is the speed in the horizontal direction? So finish reading the rest of the question. So this height is 0.34. That distance is x. And the motion is negligible again. So we have to find the speed this time. We can again use that projectile motion equation for vertical motion, because we have a change in y. So we have delta y is equal to vy initial t plus 1/2 gt squared. So because we know that vy initial is equal to 0, just like it was earlier, same problems basically set up. So we have 0.34, which is our delta y. It's 2.65. We have a change delta y here, 0.34. So we can plug that in. 0.34 is equal to 1/2 times 9.8 t squared. So that's 0.34 this will be 4.9 t squared, and then t squared is equal to 0.34 divided by 4.9, which is 0.0693878. We'll take the root of both sides here, and you'll get that t is equal to approximately 0.263 seconds. Now you need to use horizontal motion to find the speed. So x is equal to vxt. So if you solve for vx, you can divide both sides by t. You get that vx is equal to x over t. So vx is equal to 2.65 divided by 2.65 was our range, 2.65. We traveled. And then the time that passed, our t, we found over here. So you can substitute that t in here. You're going to have 0.263, and this is going to be approximately 10.1 meters per second. So that's your answer for part A. Now for part B, we're asked what is the distance h of the hole above the water surface? So we can use Torricelli's theorem. So v is equal to the root of 2gh. So if we solve for h, in this case, we want to square both sides. So we have v squared is equal to 2gh. Then we want to divide both sides by 2g. Then we get that h is equal to v squared over 2g. Now all we have to do is substitute in our values. We have that v is equal to 10.1 meters per second from a previous answer, which was v is equal to 10.1 meters per second right here from part A. And our h is going to be 10.1 squared over 2 times 9.8, which will give you approximately 5.20 meters. Now we're asked, what is the value of hg, the height of the water surface above the ground? So the water surface above the ground. So that's hg, that green. So we know that the water surface is above the hole by a height of h, and then we know that the hole is going to be above the ground by a height of 0.34 meters. So that means that for part C, we know that hg is equal to the height, which is this green. I'll change this color to something else, plus our 0.34. Now we can just substitute in. We know that h was 5.20 meters, which we just found over here. And then we know we have our 0.34, giving us a height above the ground of 5.54 meters. Now, let's move on to our next question. We have a narrow tank is emptying as shown to the right. So for this problem, our setup is going to look like this. We're going to have a narrow tank. It's going to be wider, have a larger cross-sectional area for the pipe at the top, but then it's going to get really narrow at the bottom, like this. So, and then it squirts out water like this over here. So this is going to be, we're going to call this D1, and we're going to call this here to be H1. We're going to call this to be H2, and let's call this to be D2. Our water is going to fill up this tank like this. Now, first we're asked, what is the diameter of the tank? So, for this question, let's write down what we were given. we're given that all these heights. So H1 is 1.95 m, H2 is, let's label this here, or let's just write here. H2 is 0.55 m, H3 is 2.15 m, D2 is 1.50 centimeters, D2 over D1 is 0.47. So in order to find the diameter of the tank, we're given what the ratio was, D2 over D1 being 0.47. So if we have that, then we can solve for what D1 is, because we can just multiply both sides by D1. We can cancel that D1 out, and then we have D2 is equal to 0.47 over 0.47 D1. Then we can divide both sides by D1, or we can divide both sides by 0.47. So we have D2 is equal to, or D1 is equal to D2 over 0.47. Now we know that we were given what D2 was up here. D2 is 1.50 centimeters, so we can just substitute that in here. D2 is going to be 1.50 divided by 0.47. And if you plug this into a calculator, this is equal to 3.19149 centimeters, but we're just going to round this to 3.19 centimeters. So that's what D1 was. So we're just like kind of figuring things out. Now we're asked, what is the speed of the water at the exit? So we need to compare what the water surface at the top and what the exit at the bottom is. So we know that here, this is water surface, and then this is exit at the bottom. So this tank is gonna exist inside of, on the earth, right? So it's exposed to the atmosphere out here. And we can see some characteristics about this. We know that this is an open tank. We know that it has a non-viscous fluid. So because it's going to be open to the atmosphere, that means that the pressure that the tank is going to take for all the things that are inside of the tank, it is going to have the pressure of the tank. It has the atmosphere. Has the pressure of the atmosphere. So we can say that because the water exits into the atmosphere and the tank is open, that all the pressures at the top, see, P1 is equal to P2 is equal to pressure atmospheric. So in this question, we can say that the pressure 1 is equal to pressure 2 here when it's coming out, because it's all connected to the larger pressure of the atmosphere. So it just takes the atmospheric pressure. So in order to find what the speed is, though, let's find the vertical height difference. Vertical height difference is equal to the delta y. So we have h1 plus h2 plus h3. Our h1 is our distance from the top to the narrow. And then h2 is going to be from the narrow. Let's see here. H2 is going to be this. And then H3 is going to be this. So that's going to be the narrow to the narrow. And then H3 is the top of the bottom of the narrow to the bottom. So if we can add these up. And we were given these in our equation. So we have H1 plus H2 plus H3. That's just going to equal to 1.95 plus 0.55 plus 2.15, which is 4.65 meters. Now we can use our continuity concept. We know that Vs is going to be we'll just label this as the speed at the surface. And then we can say that Ve is equal to the speed at the exit. So then we have our continuity equation, which is A1 Vs is equal to A2 Ve. So then we want to isolate for the VS, A1 over A1, and then this is going to cancel out like that. Then VS is equal to A2 VE A1. So now all we have to do is remember that area formula. So area is equal to pi radius squared. In this case scenario, we're given the diameter, not the radius. So we want to do this in terms of what the diameter is for the sake of this problem. We know that we can rewrite radius as pi times diameter divided by 2 squared. So that's area is equal to pi diameter over 2 squared. We can see that area and diameter are going to be directly related. So area is proportional to diameter squared. Now we can just substitute this into our problem. We know that in this problem, we have a ratio A2 over A1, which is visible right here. And we can write that equal to the formulas for the areas. So if this is the formula for our area, we can just write this with the corresponding diameters for the different areas here. So when you're at area 2 and area 1, you're going to have D2 and D1. And then when you see everything in this equation, everything's going to cancel out except for that D1, D2. We're going to keep that. So we're going to have D2 over D1, and we're going to square this whole thing. And this is going to be equal to 0.47 squared as our ratio. Because we were given this ratio over here. So now we can substitute that in to find our V speed. So V speed is going to be equal to our 0.47 or our 0.47 squared, and that's equal to 0.2209. So V speed is equal to 0.2209 times VE. However, we still don't know what V exit is, but we can find V exit. We can usually find our velocities using Bernoulli's equation. Find V. So our Bernoulli equation, we're going to use it from the surface to the exit. Conservation of energy from the surface to the exit. So, this is to the exit. So our equation is the pressure was atmospheric. 1/2. We can cancel out that. Now all we have to do is move our terms. So we're going to have 1/2 rho VE squared minus VSC squared is equal to rho G Y1 minus Y2 and Y1 minus Y2. We know that Y1 minus Y2 is equal to delta Y, and we know that the change in height here, we can take this is equal to 4.65 because we have our heights here, and we can see that the change is 4.65 over here. So that was the vertical height difference. So after this, we can substitute everything else in. 1/2 VE squared minus VS squared G 4.65. So we know that VS is equal to 0.2209 VE over here. So you can actually take this and then substitute it into your other equation where we see VS. And then after that, you're going to have 1/2 V squared E minus 0.2209 VE squared is equal to 9.8 times 4.65. So now you just have to do a bit of algebra and rearranging. (469 squared). So this is going to be equal to 0.09095120319 VE squared. And this is equal to 45.57 because you can take that VE and factor it out. And then you have multiplying that 1/2 times that, you would get 0.47560,159 VE squared is equal to 45.57. VE squared is equal to 45.57 over 0.475601595. And then this would be approximately 95.82. Then you would just take the root of both sides and you would get V exit is equal to 9.79 meters per second. If you wanted to avoid all these, you could have just rearranged this form first before you substituted it in as well and solve for V E first. But it's done this one. Done. So for part C, we're asked what is the speed of the water surface? So we're looking at what is VS for C. VS is equal to 0.2209 VE, but we already got what VE is. So we can just solve for VS really easily. So 0.2209 times VE, which we just found right here, 9.79. 9.79. So that's going to give us approximately 2.16 meters per second for our VS. Now, for our next question, we have a different setup. So this is going to be like a cylinder. This is going to be height to the ground. And then we have at this point here, water coming out. We'll call this distance X. And then we'll call this height. And this is to the point that the water is filled up in the tank. So let's read this question. The motion of the water surface needs to be considered when the diameter ratio is 0.44 is greater than 0.44. So the height of the stream above the ground is equal to 1.15 meters. So here we have that it's 0.53. So because d exit over d surface is equal to 0.53 and 53 is going to be greater than 0.44. So that means that motion of the water can't be neglected. So we have to use continuity, Bernoulli, and also projectile motion for this question. So let's write down what we have. In this problem, they give us that the height of the hole above the ground, so this is going to be y of the hole, that's equal to 1.15 meters. And then the hole is above the water's surface, is below the water surface, by 2.10 meters. We know that the diameter of the hole, this is given as 2.8 centimeters, aka 0.028 meters. And then we have our ratio d exit over d surface, and we're also given density, 1,000 kilogram per meter cubed. This is water. We also have the pressure of the atmosphere, 101.3 kPa. So we're asked first, what is the diameter of the tank? The diameter of the tank, we have what the ratio of the diameters are. D exit over d surface is equal to 0.53. So we can use that to get the tank's diameter. So we know that d of the surface, we could rearrange this, is equal to d exit over 0.53. If you flip these, then you get d surface over d exit is equal to 1 over 0.53. And then if you multiply both sides by d exit, then that multiplies there, and then that's how you get that. So then we know that d at the exit down there is 2.8 centimeters, right? So then you can divide that by 0.53, and then you would just get 5.28 approximately as the diameter that is at your surface in centimeters. You can convert it into meters as well. That would be 0.058 meters. Now we're also asked, what is the velocity of the water stream in the horizontal direction? Horizontal direction. So we have to look at what do we have in the setup. So because we have an open tank and it's not a closed system. So when you have pressure, that means you would have a closed system, but we don't have a closed system here. We have an open tank to the atmosphere. So because we have that P1 is equal to P2 is equal to PATM. And later when you have your Bernoulli equation, our pressure terms will cancel because it's equal on both sides. Pressure will cancel. And then you could just subtract it from either side, and then you would see that it would just cancel out. So here we're going to let Vs be V speed of water down, of water going of water surface down. And then we'll let that VE be the exiting speed of the stream. So our first step for this, we're going to use our continuity, which is our AS, VS, AE, VE. VS will equal to AE over AS, VE. And then we know that AE over AS is the same as our relationship earlier, DE over DS squared. This will be equal to 0.53 squared, and then this will be equal to 0.209 to 809 VE. So then we can use Bernoulli's equation. Again. So we're going to have our atmospheric pressure, which we can cancel out from both sides. So then we have this. So we know that y1 minus y2 will equal to 2.10 meters. The surface is 2.10 meters above the ground, right here. here we're going to have 1/2 v squared minus vs squared g times 210. So then we can 1/2 VE squared, just like we did earlier, 0.2809. VE squared is equal to 9.8, 2.10. So what we did here was we took that 2.09, which we found over here. So we had VS is equal to, so this was the ratio AE over AS. So then we substituted in for AE over AS. So we had VS is equal to 0.209 VE. So actually, I should just 209. So then you took this and then you substituted in for VS right there. You had that equal to 9.8. And then you had here, so simplify to point. And then you would just simplify this. This would be 0. That'll be 6.68 meters per second. If you take 20.58, take the root of this, then you take the root of the product, which was 44.687. Now we're asked what the velocity of the water level moving downward is. This is the same like we did for the question 3, which is we take the VS and then we have that in terms of VE, and then we just substitute in what we had for VE, and then it gets VS, 209, 2809. That 6.68 from over here. Now we have question part D. So what is the height of the water level above the ground? This was 210 plus 1.15. This is the above ground, and then this is water surface above hole. And this is the hole above the ground. So this is 3.25 meters in total. Now for part E, we're asked how far does the stream hit the ground from the side of the tank? So now the water is going to be acting like a projectile. So we have Vx is equal to 6.68 meters per second. We have Vy initial is equal to 0. And then we have Y initial height above the ground. You're going to be starting at the ground. So that's going to be equal to, or you're not starting at the ground. You're starting at 1.15 meters. That is the water. We're looking at what the water was. So that's 1.15 meters Y hole. Now we have to find the time to hit the ground. that's equal to delta y because we have vertical motion. We're looking at what changes our vertical motion. Vy initial t, we're going to use that cake equation that's looking at the vertical motion, plus 1/2 gt squared, because this is the one that has our time. And this is going to be 1.15, our change in y, because we know it went from the top of it to the bottom. So that's just 1.15 minus 0. So you have 1/2 times 9.8 t squared. That's equal to 4.9 t squared. So then t squared would equal to 1.15 divided by 4.9. And this is equal to 0.234694. If you take the root of both sides here, then you get that t is approximately going to equal to 0.484 seconds. Now, you need to find what the horizontal distance is. But we use, again, our easy formula for our horizontal distance traveled by using our Vx, velocity in the x direction, because Vy is equal to 0, times the time. So that's 6.68 times 0.484, which is approximately 3.23 meters for our x. So this is where the stream lands from the side of the tank. So that distance, x, is equal to our 3.23. Now, let's do another question. Question 5. Let's actually move this work up here. Let's make some room like this. So for question 5, we have a similar setup. So we're just going to take this setup and move it down. So we have 0.44, height above of the stream above the ground is 0.90. And then the diameter is 4.90 centimeters, aka 0.049 meters. We have that the water level in the tank is moving at 1.6 meters per second at this point in time. So let's write down what we have. Y whole above the ground, 0.9 meters. Diameter of the surface. So actually this is, well, it's going to be the same because it's going to be like a cylinder in this case. So it would be the same at the surface as it is at the exit. Or the exit is that hole. So that's actually a different diameter. Here that would be the exit. So this is not opened at the bottom. It's only opened at the top. So Vs is equal to the Vs referring to the velocity speed from the surface downward was 1.68 meters per second. And we have our density of water and pressure atmospheric. So we want to find first what the diameter of the hole is on the side. That's d exit over d surface. That's 0.49 as given in this part of the question over here. So d exit would be 0.49 times the surface. That would equal to 2.401 centimeters. We want the speed exiting. So we use continuity. We want to get that VE. So we can do the ratio again So we know that the ds over d2 is equal to 0.49. Now, if we flip these to get we know that dE over ds is equal to 0.49 from the ratio. That's dE over ds. But if we want to get ds over dE, we flip it, and then we get 1 over 0.49. So we're going to take exactly the ds over dE and substitute that in there. So in VE, this is equal to the ds over dE, because here we would have VE is equal to this. And then instead of this, you just substitute in this, which I'll highlight here for you. So this is this whole relationship. Plug that in there. And then this is still that VS. So then now what you have is 1 over 0.49 squared times 1.68. Now this is approximately equal to 6.997 meters per second, which we'll just say is 7 meters per second. We're also asked, how far does the stream land on the ground from the tank? So again, we want to get what our x is, our range. Like earlier, this is still going to be a projectile. So you have to find the time to hit the ground. Time to hit the ground, we use delta y, vy initial t, plus 1/2 gt squared. We know vy initial is equal to 0. So then that whole thing cancels out. We know change in height is 0.90 because we know it starts, that's the maximum that it's going to go from. So this is like the peak of the range. That's when it's at the highest y coordinate. So it's going to fall all the way down by being accelerated by gravity. So then we have 0.90 is equal to 1/2 9.8 acceleration from gravity t squared. This is going to be 4.9 t squared. And then we have t squared is equal to 0.90 over 4.9. And then that's 0.183673. You're going to take the root of both sides, and then you would just get that t is equal to 0.4286 seconds. And then horizontal distance, just like we did earlier, it's just pretty simple. You just take your vx component times our t we just found. So that's this t. And then we're going to multiply it by our vx. So our vx was equal to our 7 meters per second v at the exit. So you have to be able to identify that you had vx just by another variable named ve label times our 0.4286. This is approximately going to be equal to 3.0 meters. So that is your x. Now we're also asked, how high is the water level above the ground at this point in time? So how high is the water level? So we're trying to find what Hg is. Like, it's talking about the surface water level. It's kind of unclear, but we're basically finding Hg. So what that means is we know that we can use Bernoulli's principle between our water surface and our hole. So because we know that P1 is equal to P2 is equal to atmospheric, because it's going to be open, to this atmosphere. So it's going to take the pressure from the atmosphere. That means that you're going to have all the pressure will cancel out. Pressure cancels out. We can write that though, and then cancel them out to show. So that all cancels out. Then you just divide by both sides by P. So, or both sides by rho, because you see it in every single term as well. Now we need to get the height difference. So we're going to get these terms, and then we're also going to get these terms. So we're going to have our gy1 minus y2. And then on this side, we're going to have our 1/2 ve2 minus vs squared. So we know that we can simplify this because what we want to get is what the height is. And we know that height is equal to y1 minus y2, right? So we want to get that y1 minus y2 alone. So that 2, and then we're going to divide this by 2 as well. We can now multiply those 2's in the denominators. I mean, this is actually a g. So then those cancel out. So then you can also, here, you can plug in that h is equal to this. So we'll just write h here. So that's going to be ve squared minus vs squared divided by 2g. And then h is equal to 7.0 squared minus 1.68 squared over 2 times 9.8. Now, if you simplify this, this is just equal to 2.356 meters. Now, we know that the water surface is going to be 2.356 centimeters above hole. So that's our water surface. So was this for this question? Yes, it was. So this h is going to be equal to 2.356 meters. So in order to find hg, we have to just add those together. So our height g is equal to h plus 0.90, which is 3.256 m for our height above the ground. Now we just have one more problem. So it's going to be the similar tank problem again. So let's bring that down here. So the motion is considered when the diameter ratio is greater than 0.40. Here it is greater than 0.40. It's actually 0.57. The hole on the side is 2.30 meters below this water surface. So we have that this is 2.30 meters. And then it's 3.50 above the ground. So this is 3.50 meters above the ground. And this is not drawn to scale, so it's fine. And the diameter ratio is that. But we're not given what the diameter is. So we don't even know what the diameter is. We're given what the ratio was, though. So let's just see here. Yeah, we have the d exit over d surface. So if we have that d exit over d surface, we already know from doing this multiple times that a exit over a surface can be found using that ratio. So you're going to take that 0.57. We know that everything else canceled out, and it just ended up being d exit over d surface. And then that ratio is squared. So then we can just take that 0.57 that it's equal to, and then we square it. And then because the relationship between area is going to be d squared. So that's the proportionality in play. So that's going to equal to 0.3249. So then if you use your continuity, you're just going to get our A1V1, which was our AS VS equals to AE VE, VS equals to 0.3249 VE. And then we need Bernoulli's principle like we did earlier. So that's water, surface, and then hole. P1 equals P2 equals PATM because of the exposure to the surface. This is an open to the surface tank, so that means that pressure cancels. So Bernoulli's equation will have and then this will simplify. So we'll have 1/2 VS squared plus GH. We can also see that these all cancel out because we have just water, one fluid. When you have one fluid, the rho always will cancel. So rho equals same fluid cancels. I'll write hole over here. Let me actually write there. So then this is going to simplify to this 1/2 VE squared. And then you also start from VS, VE, GH. Our H is equal to Y1 minus Y2. So now we can just substitute in our VS here. So our VS was this expression, right? So we'll put that here. 0.3249 VE squared plus G 2.30 1/2 VE squared. Then we're gonna have 1/2 0.1055. So that's 7.1 meters per second for VE. But we want VS. So VS is 0.3249 times 7 times our VE, right? So then our VS would be approximately 2.31 meters per second. And then for our horizontal distance, we first need to get our height above the ground. So we know that Y, the height of the hole from the ground, is going to be equal to HG minus H. So that's going to be equal to 1.20 meters. And then we can find the time. So our y was y whole. So that's going to be that 1.20 meters. So p squared 4.9, or t is 1.20 over 4.9. And then that's approximately going to be equal to, taking the root of both of these, t will equal to 0.495 seconds. And then finding our horizontal distance, we are going to have x is equal to VET, which is equal to 7.10 times 0.495, which is approximately 3.51 meters. That's it.